So far in finding the t-test statistic to test for slope, we were taking the slope b1 and dividing by the standard error of b1. And so we've just been pulling that number out of the table. Another way to get the standard error for b1 is provided here. It does require us to have SSE or MSE, either of those. So we'll be able to pull those here out of the ANOVA table. We won't ever calculate SSE or MSE quite on our own, but we can talk a little bit about what that number is. And this was a concept mentioned briefly in Chapter 2. SSE is the sum of the squared residuals. Visually, when we think of like finding a fit of a line to some data points, remember the residual is the distance between the point and the line. So for every data point, we have this residual. So the idea is if I take all those distances and I square them and I add them all up, that is what SSE is equal to. So if SSE is larger, that indicates data points scattered farther from our line or like a poorer fit. When SSE is small, what we have is data points closer to our line. So if we have SSE and we divide it by n-2, that is the same as MSE. This is our MSE. If we take the square root of MSE, this is this thing we're calling S sub epsilon. Finally, once we have that number, S sub epsilon, if you take that and divide it by the standard deviation of the x's times the square root of n-1, that is how you can obtain the standard error of B1. So if we think about this picture I just drew, more scatter in our data is going to produce a larger SSE. If SSE is larger, this S sub epsilon is larger, and this is larger. That will produce for us wider confidence intervals, and then a smaller test stat or a larger p-value when we're trying to do our test. Okay, and then if it's the opposite, if we don't have a lot of scatter, we get a smaller SSE, narrow confidence intervals, and more likely to get a smaller p-value and reject and say we have evidence of a linear relationship in the whole population. Okay, so with all that being said, we're going to do a quick calculation here of this number. So S sub epsilon first is the square root of MSE. And we have already looked at this. This is the mercury pH one. Okay, so if we just go back to our table here on the previous page, MSE is this error row. We found 0.0793. So we want to put that in and take its square root. So we get 0.2816. We were also told the standard deviation of the x's is 1.28845. So our standard error of the slope is 0.2816 over 1.28845 times the square root of n-1. N was 53 here, so square root of 52. We get 0.0303, and we want to verify this matches what we were given in the output on the previous page. So 0.0303 is in fact what we were given here as the standard error of the slope.